Okay, thank you. I wasn't in this group, so I'm not really prepared to address the details there, although if we have time, I'll come back to it and do my best. We kind of started out by, we're doing measurement and validate and kind of reworded it. It's subtle, but it's pretty much the same thing, which is detect and measure correctness. So the idea is to find, you make some nanomachines and now you have to detect if they're working correctly. And here's the subsets of things you need to look at. Is it positioned right? Is it oriented right? Does it work right? You're detecting maybe motion, for instance. And then the connections too. So if your device isn't getting the right inputs, it's not necessarily going to do the right thing or do it at the right time. And if its outputs aren't connected correctly, whether it be internally to another device or external to the world, then that's also not going to work. I mean, it might come up with a great answer, but it doesn't know how to tell anyone, So you have to check the connections too, and I'll come back to this in a second. And then we looked at how we would detect these things, which gets more to, the technology that's needed in 34 in order to do this in 35, right? So some of this exists already, but it needs to, it has room for improvement. Like cell lipid pores. You can make artificial pores. And the thought was kind of like a sorting machine with balls or something, marbles or something, where the size of the hole will separate out the good and the bad maybe. And then you can even put charge and shape and so forth in the pore. And only the motor of exactly the right size and shape will fit through the pore. Things like that. We could do liquid chromatography. So you put down a bunch, your product, and you get it to propagate through like a piece of cloth. And the ones of the right mass are going to propagate the certain distance. You also could have essentially antibodies to bind to the bad ones, or there's all different ways that you can separate things that way. X-ray resonance is a more violent way to do it. So what we thought about is that if you have a bunch of motors in bulk, say, and you want to separate out the good and the bad, the resonance frequency of the good one might be different than the resonant frequency of a bad one. If you hit it with X-rays, which really you need that for the energy, but you hit it with X-rays at exactly the resonant frequency of the bad ones, they'll fall apart. And the good ones hopefully won't be damaged. That's real tricky because there'd be different bonds that have different frequencies, so it probably wouldn't work for anything real complex. And then direct observation. I mean, we can do it with STMs and just look at it. There's some challenges there, of course, one of which, capacity, throughput. But another challenge is if you have, say, a motor and the rotor's bad and it's completely surrounded by a good housing, you're not going to be able to observe with an STM the bad rotor, unless you maybe have that final assembly step of the rotor slipping in the housing after you do the measurements, I suppose. I'm going to skip point 2 for a second and go to point 3 because it's more related. We thought about the idea of how do you measure or detect, validate when you have 10 to the 10th things that you've produced and you want to find the 3 that aren't working or whatever, or 10 to the 3 that aren't working is more like it. How do you do that? And maybe you want, I don't know, for instance, you want all your motors at 0 degrees and half of them are 180 and it'll come back with an average and say they're all at 90 degrees or something. So you have to address that. And the point is try to keep the parallelism, the throughput you get with parallelism, but still be able to identify individual ones. So that's real tricky. And okay. So I just said, these two are related. Anyway, it's all these things you want to do in bulk, basically. So for triage the defects, it was kind of maybe out of scope here, but you know which ones are bad. What do you do with them? And you could destroy them, you can remove them, you can replace them, like they do with chips now, where they have redundant circuits and they wire them in. Or you can You can just mark it as bad somehow. Again, they do that with gate arrays, field programmable gate arrays, and then you just don't use it. You ignore it from there.